Hi there, welcome back to the channel. Welcome to another project video. This time I'm trying to achieve the ultimate Selenium Rectifier replacement board for tube radios with an adjustable voltage drop. Some time ago I showed you this little board, which is a replacement for the Selenium Rectifier on the tube radios that I restore. And this is to replace the typical Selenium bridge rectifiers, which come in various shapes and sizes. There's one here from AG, which is not that common. The most common ones are the Siemens ones, as you see here. And the way I designed this is that you would replace the Selenium rectifier with 4 silicon diodes, and it was shaped and sized precisely to match the more common Siemens ones. So the holes over here would match exactly where the holes are on the Selenium one. You could tie it to the board with the same holes, same hardware, and also the connection tags are the same. AC on opposing ends, negative down here, positive out there. This is the AC from the secondary of the power transformer. This is the ground output, or the 0 volts output from the bridge rectifier, and that would be the positive output from the bridge rectifier. Now, if you know anything about these Selenium rectifiers, as it rectifies and produces the B+, the rectified voltage, the drop is actually quite significant, which is why those things get hot and go bad after a while. So the way I designed this is that you can put some resistors in series with the B+ output before it comes out as the positive output of this little board. And in that way, as current is drawn, you can drop the voltage a little bit. So I've used this often, a lot. And there were a few things I wanted to change on this. One of them has to do with the fact that a lot of people like to have little capacitors, just some ceramics across the diodes to get rid of any switching noise. So I hadn't used that, and I've never used that. I haven't found it necessary, but some people like that. And the other thing was this voltage drop. The way to calculate this voltage drop would be to put a resistor in, see if it's too low or too high, and alter the resistance accordingly so that you can get the right B+ out that you require for your circuit. It works very, very well. It does. And as I said, I've been using this for ages, but I wanted a better way, a more elegant way of altering the voltage. And I decided I could do one that would be variable. Enter this version. Now, what is this? Well, we've again got the 4 diodes. We've got the 4 capacitors across the diodes, just to meet the requirements of some of my viewers. And then there's 2 things here that are, or the other components are rather unusual. We've got a trimmer pot over here, and we've got space for what looks like a transistor, or in this case, it's actually a MOSFET. And this thing is what I've been experimenting with because I wasn't sure this would work. This originated from an idea on which I've done a video before called the MOSFET B+ dropper. And I wanted to see whether this would work on here, but in a simplified or a simpler version. And I wanted to make it completely variable because if you look at the video on that MOSFET B+ dropper, it's really just a power zener that uses the MOSFET as the power element and the one that requires quite a bit of heat capacity, power capacity. And you don't have to use a power zener, which can get really expensive. But I wanted this thing to be absolutely variable. Variable as in you get a screwdriver in there and you adjust the trim pot and you get the voltage drop that you want. I wasn't sure it was going to work. I experimented, and now I'm happy to inform you that it does work. And I'll be showing you this thing in operation because I've already built one. And I know it looks like a bit of a mess, but there's method in my madness. I wanted to test it with a dummy load. So I've got a resistive load here. I've got a filter capacitor here to emulate the filter cap that you'd have on the radio. And I've got some test points over here that we can check some of the voltages. But the important thing is this thing over here. Here we've got our diodes. I haven't put any capacitors in here because, as I said, I never use them. But we've got our trim pot. It's a 10-turn pot. And I've got my MOSFET, which is bolted to the board. And it's got a bit of heat sink on the bottom, but we can actually add some more. We'll see if we need it when we test it. And I will be testing this and showing you this in operation a little bit further ahead. And once again, I want to thank PCBWay for their support of this video. They're sponsoring the video. They also sponsored these boards, which came out absolutely fantastically. I decided to go for black this time. The other ones were green. These are the ones that I probably will use when the access to these boards is facilitated, so I can very easily just change resistors. But I've also got this thing here, which is to replace filter caps. I explained it in the video where I presented this. You can use this to replace your filter capacitors as well. It just breaks off, and you've got 2 little boards that are very, very useful. So this is not being made extinct. This is just an upgrade for some of the radios where I want more precise voltage. I like this, I really do, and the boards once again came out fantastically. I really like the way everything just comes out, the way you do it, even the graphics, the silk screen, it's perfect. So once again, PCB Way, thanks for your support, thanks for the sponsorship. And let me get into some of the theory of this. If you want to jump the theory, jump to this timeline marker over here, and that'll save you quite a long time, and you can get to see this thing being tested. All right, let's get on with it. This is the typical supply section of a tube radio where you will have the Selenium Rectifier there, and that's fed by a transformer, and that transformer will have mains coming in, a secondary voltage coming out which feeds the Selenium Rectifier, and of course it's also got the 6.3 volt heater winding. Now B plus comes out there, and it is filtered by the first filter cap. I'm calling B plus that little point over there, and B minus the one on the negative side. You'll see why in a minute. Now your mains might differ depending on whether you're on the 120 volts or the 240 like we are here, but let's take an example where the secondary voltage of the transformer is 220 volts AC, and we've got the 6.3 volts heater supply as well. Now let's say for argument's sake that the 220 gets rectified and we have, say, 290 volts DC over there. That's our B plus, okay? Now when we replace this, it would seem simple enough. You take out the Selenium Rectifier, you put in 4 diodes or a bridge rectifier, a silicon bridge rectifier, and you expect to get that. Well, you don't. You get more than that, because the voltage drop across a Selenium Rectifier is much higher than it will be across silicon diodes. Across silicon diodes, what you should get is 1.4 volts DC, which means that you take 220 volts, you multiply by 1.414, which gives you the peak voltage, you rectify it, okay, and it should create, with the right filtering, about 310. And that's our problem. We have got much more voltage here, DC voltage, than we had when we had the Selenium Rectifier in place. Nothing else has changed. The only difference is that the voltage drop across those diodes has become smaller, much smaller. More precisely 1.4 volts, because it's 2 diode drops. So we've got a problem here, and we've got to get rid of, in this particular instance, 20 volts. Well, how do we get rid of 20 volts? We don't want the radio, which will be connected to this end over here, seeing 310. We wanted to see 290 or thereabouts. The simplest way to do that is to put a resistor in here, like that. Now what will happen is that the higher voltage will appear here, and as current gets drawn by our radio over here, the voltage drop across this resistor will be deducted from this 310. Let's say that we have a voltage drop VR, the voltage across that resistor of 20 volts. That means we're back to our 290, which is great, right? Problem solved. And in fact, that's what I've been doing with most of my restorations. By simply putting a series of resistors here, I've actually made space on the initial board that I designed for 3 resistors, which you can put in parallel and sort of adjust, sort of test by trial and error to see what resistor you need to get 290 volts. That is not a very elegant solution, I must admit. It's a rather rough and ready solution, and I've always wanted a better solution. And that's what I've been seeking for some time, and that's what hopefully I'm going to present to you today. Because the problem with this is that when you first switch on the radio, your 6.3 volts is there, your tubes start heating up, but they haven't heated up enough for the current to start being drawn by the radio, which means this voltage drop of 20 volts in my example here will be 0 initially because there's almost 0 current going through. And it'll slowly rise as the current slowly rises to its operating condition. And as it rises, this voltage drop rises and we get our 290 and everything is hunky-dory. And apparently this would be fine. But as I said, I want this thing to be more scientific. So what can we do to replace this resistor? Well, we've actually got a few solutions. Here's a crazy one. You could put 28 diodes in series, and with each diode drop summing 0.7 volts, for example, 28 would give you about 20 volts drop, right? A bit crazy, but it would work. That's not what we're after. This one's a lot more elegant and a lot simpler. You simply put a 20 volts Zener reverse biased like that, which means that your B plus will go through there, or the supply current will go through there. And with the 20 volt drop, it means your 310 has now become 290. That would work. No problem with that. The problem is that this Zener would have to be quite powerful, and it's not that powerful. I mean, in this case, you're drawing, what is it, about 100 milliamps, across 20 volt. It's a 2-watt Zener. It's not a big deal. So it is actually a workable solution, but it's not the one that I like. But before I show you the one that I like, I'll put this somewhere else. There's actually a better place to put this, because this Zener will be, one leg will be at 310 volts or so. The other one will be at 290. So this Zener is hot. Hot as in voltage hot. You touch this Zener to the chassis, if it shorts and it touches the chassis, it's going to short everything to ground. So instead of putting this here, you'll have exactly the same effect if you move this to the ground side, like that. Why is this one better? Well, this is why I said I was going to call this B- and not ground. This point here, ground, is actually at 20 volts above your B-, which means that you're still seeing 290 across there. Make sense? You had 310 across from B+ to B-. Now it loses 20 on this line here, and that goes to ground. So this is actually, relative to B-, this is at plus 20 volts, and that's at plus 310. Does that make sense? Think about it. 310, 0. That goes down there. That's adding 20 volts, so that's already at 20, and that's 310, so the difference is 290 to ground. This 290 is now relative to ground. And what you've done is you've just taken the Zener from a very more dangerous position over here in the high voltage side, and you've put it with one leg is actually ground, and the other leg goes to the negative of your rectifier. See that? Now, this is the basis of where I'm getting to. This is where I'm going to play with a circuit that I've used before and that I really love, but I've made a modification to it, and that is using a MOSFET. In the video that I did on it, I called it a cheapo Zener. You can actually use this in guitar amplifiers or stereo amplifiers where you are getting things like half an amp, 1 amp of current, and 20 volts drop, 1 amp of current, you're talking 20 watts, and a 20-watt Zener is very expensive, and using a MOSFET becomes a very viable solution. Now, I'm going to use a MOSFET, but I'm not implementing the simple low-power Zener solution that I presented in the video. I'm actually going to present a variable version, which I was hoping works, and I've tested it, and it does. So let's talk about that. Now, here's a circuit for our cheapo Zener diode. The first time I saw this was in R.G. Keen's MOSFET Follies. It's a page that he has on the web that shows a lot of uses for MOSFETs, and I really like this because it allows you to use a very cheap low-power Zener to create a voltage drop which will allow you to reduce the B+ on some pretty powerful amplifiers. This thing can take quite a bit of current because the guy doing the work is this MOSFET rather than the Zener. Now, all we're doing is recreating this thing over here with this thing over here. Now, I've got a video on this particular device exactly like this where I wanted to drop, I think it was 30-something volts. I'll link that above, so I won't go into the whole thing again, but basically what this does is if you put a certain Zener over here, let's say an 18-volt Zener, the drop across this will be 18 volts plus that voltage there, the gate to source voltage that switches on this MOSFET. Now the MOSFET I've got on here for this particular case is an IRF 840. It has to be N-channel for this particular case, and it has to be able to handle a certain amount of power because the heat that you would normally dissipate across here will be dissipated on this device. So heat sinking it is an issue. And then you need 2 resistors here. This is basically a grid stopper, and I've used a 220 ohm resistor on here. And this one over here is the resistor that really allows the 18-volt Zener, or any Zener that you put on here, to actually pass current and exhibit the voltage drop that the Zener is designed for. So current comes down here. This is the high voltage. Current comes down here. It biases the Zener. There's another voltage drop across here. And the final result is that the voltage drop from there, from cathode to anode, will be 18 volts plus this VGS. Okay, now I've done this before and this works great. And I could use exactly this in the Selenium Rectifier replacement for our tube radios, but there's a problem. This voltage would be fixed, and I don't really know what voltage drop I want. So I thought, well, what if I put another resistor on here? Instead of a Zener diode, what if it's a resistor? Would that work? I mean, what exactly are you doing? You're giving it a voltage drop, which in the case of a Zener is a fixed voltage drop. And the result is that the whole thing drops, that voltage drop plus that voltage drop over here, and you get a Zener effect. And all the work is done by this guy, not by the resistors. So I gave it a try. I decided to give it a try, and the final result actually works. And it allows me to adjust the voltage drop that I want by adjusting the value of that resistor. And the best way to adjust the value of a resistor is to use a trim pot. So let me show you the final circuit of what it is that I'm going to demonstrate for you today. So here's the schematic for the final product. This will replace the selenium diodes or rectifier with 4 silicon diodes. So it still has those in there. And just for those of you who've complained about it, I've allowed for 4 capacitors across the diodes to dampen any switching noise the diodes might give. I very seldom find these make any difference, but depending which diode you use, you can use that if you like. If you use ultrafast 1N4007, so it's UF4007s, that's probably better. You probably won't even need these. And so what we've got is the plus, the B plus out here, and then this would be the B minus, and the B minus then goes to the MOSFET dropper, the one side of which, as you may recall, is the ground. And that's our minus that would come out of the little circuit that's going to replace the entire selenium rectifier. So these are the 4 connections for the replacement of the selenium rectifier. The one AC line coming in, the other AC line coming in, the B plus and the minus. Now the minus is also ground in this case. Okay. Now it's exactly what you would use to replace that selenium rectifier, exactly as is. The difference is you've now got this thing over here, and this thing over here is what I've just talked about, and we've got our 220 ohm resistor over here, and now I've got a 47K trim pot over here, and my theory was, or my hope was, that as I adjust this, the voltage drop would increase. In other words, the B plus measured from here to ground would be reduced depending on how this was set. And the idea is that I could set it from anything from maybe 10 volts to 20, 30 volts. I'm not sure exactly how much range I'm going to get on this. The way I see this working is you've basically got a component here that becomes a variable resistor. The resistance between the drain and the source of the MOSFET will change depending on the voltage between the gate and the source. And you can actually use this in a sort of a variable resistor situation where if you switch this thing on, it's like 0.2 ohms or less than that, a few milliohms, okay? But depending on where this is set, this voltage is set, this thing will increase and decrease. That's why it has a voltage drop across it that is converted into heat, and it creates the voltage drop between there and there. Now, I wasn't quite sure what sort of range this would give me because, you know, if you think about it, what you've got is you've got a resistor here in parallel with another resistor between this point and this point. Now, if that is the case and this thing becomes very, very low because it switches on, you know, like let's call it 0.1 ohm, then whatever you put on there, it's still going to be 0.1 ohm. However, because this thing, if this thing goes down to 0.1 ohm across there, it can only do that if there's enough voltage on here to give it the switch on voltage and make this a very low resistance value. But that'll happen if there's a voltage across this part of the voltage divider of the potentiometer. And if you've got a very low voltage across there, you've got very little voltage on there, so that becomes 0, so that switches off. So it's a sort of a feedback situation where it stabilizes to the point where the voltage from the gate to the source will be enough to allow this thing to exhibit a certain resistance, and then there's a difference, the other voltage between here and there. So it's sort of a feedback system. This is a beautiful system. The way it works, the way this feedback loop works is fantastic, because if you think about it, if you finally got 20 volts drop between there and there, that means that about, call that 3 to 5 volts over here. That's about 15 volts over there. So you'll get about an 18 volt drop across here. Okay. Now, if this resistor range was bigger, that would alter that as well. And the one that I've found works well is about 47K. Now, what power does this thing have to dissipate? Well, if I've got 20 volts between there and there, then I've got 20 volts across the trimmer, and the trimmer is 47K, so it's about 0.4 milliamps. And if you work out the power consumption or the power rating of this trim pot, 0.4 milliamps at 20 volts drop across it is about 0.008 watts, if my sums are right. So very, very little power is dissipated on here. This thing practically has no current flowing in, so this is a very low wattage resistor. You know, it can be a quarter watt. I normally use a 1/6 watt, and this is where the power is dissipated. And you've got to get a MOSFET that can handle the current, which won't be much in this case. It's about 100 milliamps, I think. And there will be peaks when the capacitor's charged, but it's not a big deal. Then the voltage drop. So you're looking at perhaps 2 watts over here. And there's one other advantage here, and that is that the drain is actually the metal tag at the back of the MOSFET. So that can actually be connected to ground, where ground would act as a heat sink. The way I've done it in the PC board, in the board itself, it doesn't quite work like that. You don't have to connect this to ground, but you can do that if you want to. Let me show you what the board looks like. This is the same size as the other one. It fits perfectly into the holes between there and there of the other selenium rectifiers, the most common ones used on these radios. And we've got the 4 diodes as usual. We've got the space for the 4 capacitors over here. There's that other capacitor that would dampen the voltage drop across the MOSFET. There's our 220 ohm resistor, and there's our MOSFET, which is laying flat on a metallized or a exposed piece of the PC board, so that we can use that as a heat sink as well. And it fits pretty well. I mean, it fits perfectly on here. Let me show you what this thing looks like in 3D. Here it is. That's what it looks like. And you see the MOSFET itself. The actual heat sink is the drain, and that happens to be ground. So if you connect this whole thing to the chassis, you're not going to damage anything. You might not want to create a ground loop, so you might not want to do it that way. But this is what it looks like, and that's it. And the underside is also exposed, so we can get a bit of heat dissipation on here. I think for the amount of power this thing's going to be dissipating, the actual heat sink or the actual heat sink here and the part of the board that's exposed on the top side and the bottom side will probably be enough to keep this thing safe. But we can then always test it and find out. But that's it. It looks neat. It looks great, and now I've just got to experiment and show you how this thing operates. I'm not going to be able to put this on my Brown because my Brown doesn't have a full wave rectifier, but I'll be able to use this on all my other radios. Okay, let's see this thing in action. Okay, let me show you what we've got here. We've got the board done up. I've got the positive coming out here, and I've got the negative coming out of the respective negative pin on there. I've got AC in, the 2 blue ones. They're going to my variac and isolation transformer. So this is going to emulate the transformer secondary. There is an isolation transformer on there. There's a dim bulb limiter on there. And the variac I can bring up very slowly, and I'm going to start it at 50 volts. So that's the AC coming in. And then the DC out, the B plus out, would be these 2 coming out here. Now they're going to these 3 resistors. These 3 resistors are 1K 25 watt each, I believe they are. Yes, 1K 25 watts. So I've got 3K in series. So if you can imagine, if I have 100 volts over here and I've got 3K in series, I'm going to be passing 33 milliamps. If I've got 200 volts on here, I'll be passing 66 milliamps. I've put this 47 microfarad 450 volt cap on here to filter that, to emulate the filter cap on the radio. And one of the meters is going to measure the output voltage. This is the voltage that we'll be getting from our little board over here, okay? So little brother is measuring the output voltage, our B plus voltage coming from the board, and big brother over here is connected to the actual output of the bridge rectifier. So it is these 2 wires, and I've just connected them to the positive and negative of that bridge rectifier, so we can see what voltage we have before we start dropping it across the MOSFET using that trimmer resistor, the trimmer pot. I've actually placed another capacitor across that particular voltage, so the voltage from the bridge rectifier, because if I don't actually filter that, we won't see the drop accurately on the meters, because there'll be a hell of a lot of ripple at this section. The ripple's only being filtered after the trimmer and the MOSFET. I wanted to see an actual depiction of DC voltage. So this thing is just sitting in the back there. Be careful. That thing's got a high voltage on it. So what I'm going to do now is I'm going to start this thing at 50 volts AC coming in, and we'll see what our voltages are. So those voltages should be visible. Be very, very careful. This is going to have high voltages on here. So if you're doing this, you're doing so at your own risk. I don't want to get zapped. I don't want anybody else to get zapped. So be very, very careful. And if you don't know what you're doing, stay away from this. All right. So let's switch on the dim bulb limiter with the isolation transformer with 50 volts coming in here. And what this is showing us is the actual voltage from the bridge rectifier, 71 something, 72 volts. And the voltage we're seeing at the output of that little circuit going to the load is 52 volts. The other thing we can see here is that that filter cap that I put at the output of the bridge rectifier is doing a good job because I've only got 0.4 volts ripple. So that gives us a good indication of what we can expect. And also, one more thing to notice. If we take 50 volts and we multiply by 1.414, we get like 70 something. So that's not far off. That's more or less where we expect to be anyway. And this here is the one I want to show you altering as I alter the trimmer. So how am I going to do this? Let's try it like this. I'll be altering here and you'll be seeing the result on there. So again, very, very carefully, I've got to adjust this trimmer, and let's say I want to give it a differential of, let's say 10 volts. Now at this point, this load of 3K is seeing 50 volts. 50 volts at 3K, it's about 16 milliamps. So it's not even warm. So I can go up quite a bit. But I want to drop that difference to 15 volts. So what do I need? 56? I'm just adjusting the trimmer pot. $56 to 71. There's a 15 volt difference. Now what I'm going to do is I'm going to put you onto the meters, and I'm going to start raising the AC voltage. So emulating a higher voltage coming in from the secondary of that power transformer. So let's see what happens then. Right, are we ready? I'm at the variac and I'm going to put it up to about 80 volts. Remember, I'm in Portugal, so my mains is 230 or so. It's now at 80 volts. And what we're seeing here is 110, 95. So again, we're still at 15 volt differential. Let me go up to 100 volts. There's 100 volts. That's pretty good. 119, 134. We're back to our 15 volts. So it's doing its job. And now I'm going to take it up to 150 volts. $150 volts. I've got 197, 180, so 181. That is about 16 volts difference. So it's kept pretty close to our 15 volts. Imagine this would be the same as if we had a 15 volt Zener. But even the 15 volt Zener would not give us always the same voltage drop, because the actual voltage drop across a Zener alters with varying current. So this is doing a hell of a good job. And I'm going to take it up to 220 or 200. I don't want to go too much above that. 200 volts AC. Because obviously these resistors are going to start getting quite warm. So we're at 259 and 242, 43. So we're at 16 volt differential. And that thing's working very, very well. Now, if I want to make this drop bigger, I'm going to just watch the meter. Actually, what I'm going to do is bring it down a bit, because those resistors will be cooking. I'll bring it down to about there. Okay. The ACN is 153. So we're at about 15 volt differential. Now I'm going to give it less and more. Let's say that I wanted to drop this to 175 volts. Wrong way. I'm just turning the trimmer. And because this is a 10-turn pot, it's doing it nice and slowly. There's our 25 volt differential. And if I wanted less differential, remember, the more differential I have, the hotter the MOSFET's going to get as well, because the voltage drop across it is going to increase. Let's say I only wanted 10 volt difference. So I'm going to take that up to 190. And I'm just turning the trimmer. There's 190. I've got 10 volt differential. And that is bloody nice. That is working fantastically. Now, what temperatures are we seeing here? This is not exactly an accurate way of checking the temperature of this thing, but it'll give us an idea. The resistors are at 43 degrees C. And the MOSFET, let's see what's the hottest part we can see here. 33. Yeah, it's not hot at all. Let me go a bit closer. About 33 degrees. Now that is with our 10 volt difference. Obviously, if I made this like a 30 volt difference, that would cook a lot warmer. But that's it. The heating is not an issue at this stage, at these settings, at this level. Every case is going to be slightly different depending on how much voltage drop you create across that. But of course, because these holes match precisely with the holes that you would remove the old Selenium rectifier from, you can also just pass this through a metal spacer and bolt it directly to the chassis, because that is your ground. That is your drain of the MOSFET and your ground, the ground output, the black wire. Okay. Yeah, I'm really pleased with this. I really am. In fact, I can now comfortably place this or post this on the share section of the PCBWay website. So if you want to order your own, you can just click on the link in the description below and order from there. You'll also be able to get these schematic and Gerbers from that share site and do with them what you will. And that is it for now. I'm really pleased. I've got a few of these boards that'll see me quite happy for some time, but when they run out, I'll just order some more. And I want to once again thank PCBWay for the sponsorship of the video and the boards and all the support they've given this channel. And that, folks, is where I leave you. I hope you've enjoyed that. And if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links are in the description below. Once again, thanks for watching. Bye for now. And most of all, stay safe.